In this video, we'll look at the lecture notes for section 1.5 on vibrations of a string. Imagine a string of length L fastened at its ends. So this string here has length L, and we're imagining that its ends are fastened at the two endpoints, which we're calling here A and B. So these are fixed. Let U be the vertical displacement of each point at a given x and a given time t. So if we fix a specific time t and look at a specific x, then the vertical displacement is given by u at xt. This is our vertical displacement function. We're going to make some assumptions about it. The first assumption is that we're going to assume that the displacements are reasonably small. The second assumption is that we're assuming the motion is in the plane and only vertical. So that means we're only moving up or down. There's no left or right motion. The third assumption is that the tension t at xt is directed along the tangent to the displacement profile, which is u, at x. The tension is the force on the segment to the left of x caused by the segment to the right of x, and we're assuming that it's in the tangent direction. We let theta at xt be the angle between the tangent and the horizontal, so this angle here. We remark that if that's true, if theta is the angle between the tangent and the horizontal, then tangent of theta is equal to the derivative of u with respect to x at that xt. This just comes from the fact that the tangent line has slope equal to the first derivative with respect to x. We can see that if we look at a triangle. So imagine that we have a function, and here's our tangent. If we imagine that the slope of this line is equal to m, then we can draw the base of our triangle and the height of our triangle. And this is our angle theta. Now what does the slope mean? It means that with every increase in x by 1, so if this is an increase by 1, then the increase in y is m. So in other words, tangent of theta is m over 1, which is m. So if theta is the angle made between the tangent and the horizontal, then tangent of theta is equal to the slope of the line. But the slope is given by the derivative, the first derivative with respect to x. So that's where this equation comes from. What other assumptions do we want to make? The mass of a segment at any time t must equal its mass in equilibrium position. This is known as the mass balance assumption. If we let ρ be the density at x at time t, then this assumption means what you see here in this integral equation. So this segment here, this is an arc length element. If our string was completely horizontal, then we would just have the dx here. But since the string is stretched, it is displaced, we need this element here. This measures the infinitesimal arc length because it's no longer horizontal, so it's stretched a bit. So this measures the infinitesimal arc length, and we multiply it by its density in order to get the mass. Now the segment on the right here is precisely the portion where the equation where the string is in equilibrium position. So in this case, we're looking at just the horizontal segment, so it's just a dx. We're looking at equilibrium position, so that's when we're starting out. That's when t is equal to 0. So that's what we have here. T is equal to 0. So ρ at x comma 0 is density at rest or at equilibrium. Just for notational convenience, we're going to call that ρ sub 0. So the mass balance assumption tells us that the mass of a segment at any time t is equal to its mass in equilibrium position. The mass in equilibrium position is what we have on the right. So the thing that we have on the left is the mass at time t. Now this is any segment, the mass of any segment. So this A and B are chosen arbitrarily. In other words, this integral equation must hold for any segment AB. The only way that can happen is if the integrands themselves are equal. And so that's the conclusion that we draw here. Our fifth assumption, we're going to assume that the tension T is the only force acting on the string. What does that tell us? Let's take a look at our string. So suppose that this is our string here, or at least a segment of the string. And let's look at a point x. So at this point on the string, we have a certain tension which is moving in the tangent direction. There are two components to this vector, the vertical and the horizontal. Let A be the length or the magnitude of the horizontal component, and let B be the magnitude of the vertical component. So A and B are not vectors, they're the size of the vectors, they're the length of the vectors. So we can actually determine what A and B are in terms of our known quantities. So for example, if we want to determine the value of A, we just use the cosine. Cosine of theta, remember theta is this angle right here. Theta is the angle between the tangent and the horizontal. So cosine of theta is the adjacent side, A, over the hypotenuse, which I'm calling t. So here t is equal to the size or the magnitude of t, x comma t. Just for notational convenience. T really is a vector, so it should have an arrow over it. But at any rate, so solving for A, we get that the horizontal component has size t times cosine theta. Now, the important thing to understand here is that since there is no horizontal motion at all, the horizontal forces must balance. That means they must be the same at every point. So if we pick another point, say over here, and we call this x2, then we can find the tangent vector here. We can find the tension vector t at x2 comma t, and that will have a vertical and horizontal component as well. Since there is no horizontal motion, the horizontal forces must be the same at point x2 as they were at x. So this length must still be A. This one doesn't need to be the same as B. So it does not need to equal B. This value, this length here, might be different than this length here. The vertical displacements, the vertical forces rather, might be different. The horizontal forces must be the same. They must balance out. What does that tell us? That tells us that this length, A, this horizontal component, the size of this horizontal component is independent of x. It does depend on t, but it doesn't depend on x. So if we look at this value, which is the size of the tension times cosine of theta at a given x comma t, the value doesn't depend on x, it just depends on t. So that means we can define a new function, which we're going to call tau, which depends on t only, and that's equal to the size of the tension times cosine of theta. The next thing we wish to do is apply Newton's second law. The rate of change of momentum of a body is directly proportional to the force applied to the body. Well, really, what we want to apply is the statement that the rate of change of momentum of a body is, I wasn't supposed to delete it, I was supposed to cross it out, is equal to the net force acting on the body. That's what this should say. Because what we've been talking about is the net force acting on the body. We've just shown that there is no net force acting horizontally. There's only a change in force in the vertical direction. So we're going to explore that. So first, let's consider an arbitrary interval from A to B. Now, Newton's second law tells us that the rate of change in momentum is equal to the net force acting on the body. The net force acting on the body, as we'll see, or as we have seen, is completely vertical. So what about the rate of change of momentum? So the rate of change in momentum of a segment from A to B is given by this expression here. Now, the d by dt, that gives us our rate of change, our change over time. Now, the integral itself is what gives us the momentum. Momentum is mass times velocity. So you can see the velocity term right there. The mass comes from density times this arc length component, or this arc length element. This gives us the infinitesimal expression of the mass. And when you multiply it by the instantaneous velocity, that gives us the infinitesimal expression of momentum. Now, we're interested in momentum over the whole segment, so we integrate from A to B. And that gives us the total momentum, but we're interested in the rate it's changing over time, and that's why we have that derivative with respect to t there. Now, according to Newton's second law, this is equal to the net force acting on the body, so we need to figure out what that net force is. There is no change in the force in the horizontal direction, so there's only a change in the vertical direction, and so that's what we're going to explore in this picture that you see here. Now, this is the same picture that we saw before, except that we've just isolated an arbitrary point A and B. The only thing we know about A and B is that A is less than B, but other than that, they're completely arbitrary. So at each one of these, A and B, we have a point on the string, or we have a displacement, which is what is represented here. This distance, this is our displacement, so this is u at b comma t. And there's, of course, one over here too. This is u at a comma t. So at a fixed time, we have these displacements, which look to be roughly equal, but that's completely coincidental. All right, so what do we have in the picture? Well, this t is our tension. In the previous picture, I was thinking of it as a vector, but really, I'm only interested in t as a quantity, as the size, which is why I don't have arrows here, which is, although I put arrows on this one, as you can see. So what we're interested in here is the size. So t represents the length of that vector. And we've already shown that the horizontal component has length t times cosine theta, and we saw that that was independent of x, independent of the point x. What about the vertical? What about the vertical components here? Well, those we can compute again using trigonometry. In the same way that the horizontal component was t times cosine theta, the vertical component is t times sine theta. So in other words, the vertical force at A is t times sine theta, where t is evaluated at at and theta is the angle at at. Remember, theta is the angle between the tangent and the horizontal. So we have the vertical force at A and the vertical force at B. Now, Newton's second law tells us the rate of change of the momentum, which we have here, is equal to the net force acting on the body. And again, there's only vertical force. There's only a net vertical force. So that's just the difference between these two quantities, the vertical force at A and the vertical force at B. That will give us the net force, which you can see here. So let's rewrite all of this. One of our earlier assumptions was the mass balance assumption, and that was a statement about rho times this arc length element. If we just go back to assumption 4, the mass balance assumption here told us that, as a result of the mass balance assumption anyway, we saw that rho times the arc length at xt was equal to rho sub 0, which was the density at equilibrium. So this expression here, this rho times the arc length, is going to be equal to the equilibrium density. Don't forget that there's this mu sub t there. So this times this is equal to this. But we don't want to forget that this speed term, this acceleration term is there. We don't want to forget that. Now what about on the right? On the right, we're just going to rewrite sine in perhaps what you might think of as an unusual way. Here we're writing sine as cosine times tangent, tangent being sine over cosine. So cosine times tangent is the same as sine. So we're just rewriting that for this term at b and also this term at a. The same thing. Okay, well, what are we going to do with all this? So the left term we've just rewritten here in terms of the equilibrium density. Now what about on the right? On the right we have the difference of these two, and so we've just got the difference of those two right here. Now notice that the first term has a t times cosine theta. That's what we were calling tau. So we have a tau at t. And over here we have a t times cosine theta, so that's also tau. Remember, it doesn't depend on x. So here we have an a, and here we have a b, but tau is independent of the x value. So it's just tau evaluated at t. Now what about these tangent terms? So remember, one of the things we showed very early on, we defined theta to be the angle between the tangent and the horizontal. And as a consequence of that, tangent of theta was equal to the slope of the tangent line, which is the partial derivative of u with respect to x. So we've just rewritten these terms in this way. So that's what we have here. We just have the derivative with respect to t of the integral. So let me just highlight. So that thing is equal to that thing, and this thing is equal to this thing, and let's say that one is equal to that one. Okay. Now the next thing we do is we factor out this t at tau. So that's this term right there. We haven't done a whole lot on the left, except we used the Leibniz formula for integrals again, and we took this derivative with respect to t and brought it inside. We can do that because this is an integral with respect to x, and because everything is sufficiently continuous and differentiable. So you can bring this d by dt inside the integral, and so the thing that you're differentiating is the integrand. Now rho sub 0, that's the equilibrium density, which doesn't depend on time. The only time dependence is here, the velocity. So you differentiate that and you get the acceleration, u sub tt. So that term, we differentiate it to get that term. Now on the right, we factored out tau, and so that gives us the derivative of u with respect to x at b, comma t, minus the derivative of u with respect to x at a, comma t. And for that, we apply the fundamental theorem of calculus, perhaps in the reverse order that you're used to. That's equal to a definite integral. The definite integral of u sub xx, the second derivative. So the definite integral of the derivative, in this case the second derivative, is equal to the net change in the first derivative. So we're just applying the fundamental theorem of calculus there. So what do we have? We have that this equation is true for any interval AB. AB is arbitrary. So what that means is that the integrands of these two integrals must be the same. See, this is an integral from a to b, and this is also an integral from a to b. Of course, we should put the tau back in, so this is equal to the integral from a to b of tau at t times the second derivative of u with respect to x comma t dt. It barely fits in there. But we have two integrals over the interval ab, which are the same, regardless of what ab you pick. So that means that these integrands must be equal. So maybe I'll even choose a different color. Let's go back to blue. So this integrand must equal this integrand. Actually, that's really hard to read, so I'll just underline them. So that integral, or that integrand is equal to that integrand. When you have two integrals that are equal to each other from a to b for any interval a to b, then if you have continuity, you can conclude that these two integrands are equal. So this equation is true for any interval from a to b, as we said, so we have that these two things are equal. Okay. Now this is true for any x between 0 and L. Remember, L is the length of our string, and for any time t. At this point, we make another assumption. We're going to assume that tau is constant. So tau is constant, so that's our new assumption. So that just means that this tau is constant. So what do? We get all of the constants on one side, so I'm going to divide by, well, that's not a constant, I'm going to divide by the equilibrium density. And so what do I have? I have our equilibrium density in the denominator on the right. So we have the second partial derivative of u with respect to t is equal to tau sub 0 divided by the equilibrium density at x times the second derivative with respect to x of u. So now we let c0 of x be equal to the square root of this coefficient. Why do we do that? Because then our equation becomes the second derivative of u with respect to t is equal to c sub 0x quantity squared times the second derivative of u with respect to x. So in many applications, the density is constant, the equilibrium density is constant, which is why I accidentally called it a constant earlier. In many applications, the equilibrium density is constant, in which case this quantity C0 at x is constant as well, and so we just call that C0. This constant is called the wave speed. So that gives us the wave equation. The wave equation is the differential equation you see here. The second partial with respect to t is equal to the wave speed squared times the second partial of u with respect to x. We also have boundary conditions. The boundary conditions come about from the fact that the string has its ends fixed. So at 0, the displacement is 0, and at L, which is the other endpoint, the displacement is 0. The string has its endpoints fixed, so there's no displacement at 0 and L. To determine a unique displacement, we need both the initial position and also the initial velocity. So the initial position is some prescribed function, and the initial velocity is also some prescribed function. Together, these give you the initial conditions you need in order to determine the unique displacement. Now, that's with the boundary conditions as well. So that's why this is an initial boundary value problem. And we'll solve this initial boundary value problem in Chapter 2.